difficult to film this lesson and then realized I forgot the iPad. So we're going to try it this way and we'll see how it goes. Hopefully it'll go well. We won't do this every time. This is just kind of because I made a silly mistake. So we'll see how this goes. Let me know if this is really, really bad or if it's not the worst, and if it has to happen every once in a while, it's okay. Okay, so we're going to do science. So go ahead and open your textbook to page 492. We're on chapter 11, lesson 2, which is on changing motion. So right now, let's just look at this page and let's take a look and wonder. It says, a pitcher throws a fastball towards home plate. The batter prepares to swing. Then contact. The baseball flies off into left field. What caused the motion of the baseball to change? So what I want you to do right now is I want you to think about this, especially based on what we talked about in the last lesson. Try to think of what you think may have caused this, the actual physical object that caused this change in direction or this change in motion. If you need to pause, go ahead. If not, we'll go ahead and turn the page and we'll look at page 494. And let's read the main idea together. Unbalanced forces change the speed or direction of an object's motion. And we'll learn about what unbalanced forces are in this lesson. So right now you may be saying, well, that main idea doesn't make much sense to me at all. But as soon as we finish this lesson, you'll understand what they mean. So let's go ahead and start reading. How do forces affect motion? When a batter hits a baseball, he or she applies a force. Other forces are at work too. How do all the forces acting on an object affect its motion? So, first of all, when a batter hits a baseball, so first the pitcher threw that threw that ball. So that's that first force, was that push or that throw that the pitcher made on that ball. Then what happens is there's the batter with his bat, and then he swings the bat, which is another force of motion, his body actually swinging, and it makes contact with that ball, and then that ball, hopefully if he's a good batter, flies off into the distance. Balanced forces. When you put, when you put a heavy backpack on your desk, the backpack does not move. If you just set it on your desk, you set it on the flat surface, it's a flat surface, there's nothing really there, it's just going to stay there. It's heavy, it's going to stay on that desk, it will not move. Gravity, which we learned about in the last lesson, pulls that backpack towards Earth. So it's pulling it down. It's on top of the desk, but gravity is pulling it towards the Earth. But your desk is in the way. So then your desk stops that backpack from just falling to the ground. It can't go through the desk is in the way. The desk pushes up on the backpack with a force. The strength of that force is exactly equal to the pull of gravity. We describe these two forces as balanced. Now what that means is the strength of the gravity pulling that backpack and the push of that desk on that backpack, they're balanced. It's the same. Otherwise, if the pull of the gravity was stronger, the backpack would just go right through that desk. It would break through that desk to get down closer to the surface of the Earth, to the ground. If the force of the desk was more than that pull of gravity, the push of the desk was more than the pull of gravity, that means the desk would be pushing your backpack up into the air. And we know that's not something that happens because those forces are balanced. They are the same. Balanced forces are forces that cancel each other out when acting together on a single object. So that's our first word. Go ahead and write, you know what, I'm just going to write on this mirror. I don't know if you're going to be able to see it, but I'm going to write the title on the mirror. So then at least I can leave that. So we are on, I don't know, let's cross our fingers that this works. Chapter 11, lesson 2. Oh, you can't even see that. Just go ahead and write chapter 11. Chapter is spelled C-H-A-P-T-E-R, 11, comma, lesson 2. Lesson is spelled L-E-S-S-O-N, and then the number 2, of course, and today's date at the top. because I don't think you can see that. I tried. Oh well. Okay, so our first word is balanced. That does not have to be capitalized. I just realized I only capitalized it because that's how it is in the book, because it's the beginning of a sentence. It does not have, it's not a proper noun. It was only capitalized because it was at the beginning of the sentence. Balanced forces are forces that cancel each other out when acting together on a single object. So, it's like that story of the backpack. But you know what? I'm going to use this box of chalk that Julie's mom gave me. Thank you so much. I used it on the porch. On my desk. Oh, my sidewalk. I hope everybody got a chance to see it. If not, I'll post a picture. This box of chalk. We're going to use this instead of a backpack because I don't have a backpack nearby. I'm setting it down. It's kind of heavy because there's a lot of chalk in here. I'm setting it down on the desk. It's not moving. Or this table thing. This is my grandmother's. It's not moving. Because right now what's happening is the desk is pushing up on this box so that it doesn't fall through, while gravity is pulling down on it, pulling it towards the ground. But the desk and gravity are working together, and they are a balanced force. So this cannot be pulled so hard by gravity that it goes right through the table. It breaks right through the table, and it's not being pushed by this table so hard that it's floating up into the air. It's flying up into the air. They're balanced. So they're both working on this box to keep it in its same place. They're kind of that push of the table and the force and the push of the table and the pull of gravity are canceling each other out. So this just stays in one spot. So even though there are forces on it, because they're both balanced, it's like nothing's happening to it. Each force is equal in size and opposite in direction. The pull is the same size. The pull of gravity is pulling down with the same amount of force that this table is pushing up. So it's equal in size and opposite in direction. Balanced forces do not cause a change in motion. They're canceling each other out. They're making the other one not matter. When an object is sitting still, all of the forces acting on it are balanced. So if you can see my marker, right now, it's not moving. Because the push of this book and this ottoman and this chair underneath it that I'm using for my podium are pushing on it with the same amount of force, but in opposite direction as gravity is pulling it down to the ground. Now if I do this, well now, there's one force, the force of me going back and forth, that's not canceling out. So it's not all balanced. Right now, the book is still, gravity is pulling, the book is pushing up, so all the forces are balanced. Let's look at this picture of the cute little puppies at the bottom of page 494. If the puppies pull with equal force, the ring does not move. So if they're both pulling just as hard, the ring isn't going to move. The forces are balanced. But if one puppy pulls harder, then the ring moves towards him and the forces are no longer balanced. He's pulling harder. But if they're balanced, both puppies are pulling the same amount they are using the same amount of strength, but they're pulling in opposite directions, so it's staying still. Then if this puppy starts pulling harder, well now the forces are imbalanced and the ring is going to move. Okay, now let's go to the next page. Unbalanced forces. This is the term that we heard in the main idea, so this is probably where we'll figure out what they were talking about. Suppose you push that heavy backpack across your desk, or this heavy box of chalk across this table. There is friction between your backpack and the desk. The force of friction is weaker than your push. How can you tell? Because the backpack moves. So, as I'm pushing this across this table, there's like these little placemats on here, so they're causing even more friction. So as I push it across this placemat, I can feel that especially right there, this placemat, the friction is this friction is there. I can feel it. This friction, remember friction is what happens between the surface of two objects to slow it down or stop it. I can feel, especially when I get right here, that there is that friction. But my push is stronger because I'm still able to move it. If the friction was stronger, like it is in some of these places, the box stops until I put a little more pressure on it, and then I am stronger than the friction again. Forces that are not equal to each other are called unbalanced forces. Unbalanced forces cause a change in motion. The direction of motion is towards the greater force. So whichever is pushing the greater force is the direction that the object will move. So as I'm moving this across the placemat, my push is moving in this direction. The friction is kind of moving up towards it, stopping it. Between the two, just making it stop. So because my push is stronger than the friction, it's moving, they're unbalanced forces, and it's moving in the direction of my push. So let's condense all of that into one definition. So number 2 is the term unbalanced forces. And let's put that whole paragraph, that whole short paragraph into one definition. So first of all, forces that are not equal, that cause movement in the direction of the stronger force. So right now on this box of chalk, the forces are balanced. Gravity is pulling just as hard as this desk is pushing. But now I'm going to make them unbalanced. My push is stronger than the friction of this placemat. So it is still moving in the direction that I am pushing because my push is stronger. Over 300 years ago, the English scientist Sir Isaac Newton told how force and motion are related. Today, we measure force in metric units called newtons. The newton is named after that famous scientist. So, our word number 3, and I think our last vocabulary word, is Newton. And what that is the metric unit used to measure force. And the abbreviation, because all units of measurements do have abbreviations, we will especially see that in our next chapter of math. The abbreviation is that capital N. Okay, I'm going to give you a second to write all of these down. I'll go ahead and move the iPad closer so that you can see them and make sure you have them written, because I know they might not be super easy to see right now. So I'll pause so that you can write the definitions, and I'll do a close-up that you can pause it on until you get all those definitions written, and then we will move on. to the book. Weight and force. You may recall that the Newton is also a metric unit for weight. How are weight and force related? An object has weight because the force of gravity pulls down on the object. Therefore, weight is a force. Like all forces, it is measured in newtons, in the metric system. So, newtons are the same for weight and force because weight is a force. Remember, weight is how much gravity pulls on an object. So, we know that gravity pulling on an object is a force, so that means weight is a force. Now, let's look at the diagram at the top of the page and make sure to pay close attention because you may see it again. So what it says, we have the title of this diagram is Newtons of Force, and we see a book, a bottle of water, an orange, and some tennis shoes. So we know the newtons of this book are 15 newtons, so that's how much force is on this book. And the water bottle is 5 newtons, the orange is 1 newton, and the tennis shoes are 10 newtons. And then we see we have an empty backpack to the side, which the force of the empty backpack, it weighs 5 newtons. So now what we're going to do is you are going to choose the items you would want in your backpack. How much force would you need to lift the backpack? So what you do to figure this out is you pick the items you want to put in this backpack. Let's say you want to put them all. You need all of them. You need your orange for lunch, you need your book for school, you need your water bottle and your tennis shoes for basketball practice after school. So you're going to put them all in your backpack. And you have to figure out how much force, how many newtons of force you need to lift that backpack. Well, what we have to do is we have to add all of these objects, the newtons of all these objects together, plus the empty backpack. And that's going to give us our total force. So the book is 15 newtons, and then if we add the water bottle, that's 20 newtons. Then if we add the orange, that's 21 newtons. And then if we add the tennis shoes, that's 31 newtons, but that's just the objects inside. Now we have to figure out, we have to add in the empty backpack, which is 5. So we have 36 newtons of force needed to pick all of those up. So what I want you to do now is I want you to find 4 similar items around your house. Try to think of something that if you don't have an orange or a water bottle, think of something around your house that's it feels like it might be the same weight. It doesn't have to exactly be, but an idea, because I know you have tennis shoes and I know you have a book around. So if you don't have an orange, you can use like an apple, or maybe if you have those little cuties, you could use like 2 of them. Something like that, tennis ball, whatever. If you don't have a water bottle, maybe like a small can of vegetables or soup or something might work. And get your empty backpack, and I want you to feel what about 36 newtons of force feels like. After you're done, well, you can do that after this lesson, but I do want you to try that. Now, let's do the quick check. Remember, that's where I ask the questions. You pause the video and answer it in your notebook underneath your last vocabulary word, and then you play the video and check your answer. You're doing this in pencil, so if you end up with an incorrect answer or an answer you're not quite sure is right, you can go ahead and change it. I don't need to see corrections. So the first question, predict. If the brown puppy, okay, so we're going over to this picture of the puppies. If the brown puppy pulls the ring twice as hard as the black puppy, what will happen? Why? So now go ahead and answer that question. Make sure you say what's going to happen and why, and then play the video to find out if you are correct. Okay, so what's going to happen is that ring will move towards the brown puppy because if he's pulling twice as hard as the black puppy, the forces are not balanced. And so remember, unbalanced forces on an object mean the object is going to move in the direction of the greater force. Well, the brown puppy's force is pulling 2 times as hard, so that means its force is 2 times greater. So that ring is going to move towards the brown puppy. Now the critical thinking question, same thing. I'll finish reading it, you pause the video, and then write your answer, and then play it when you're done. A steel ball is placed between 2 magnets of equal strength. Does the ball move, and why? Pause the video, make sure you answer, does it move, why, does it or does it not move, and then play. Okay, so the answer is that steel ball is going to stay in the same place. It's not going to move between the two magnets because the pull of those magnets on that steel ball, since they are of equal strength, it's a balanced force. They're both pulling in opposite directions at the same amount of strength or force. So that means that ball is not going to move. What would have to happen is one magnet, in order for that ball to move, one magnet would have to be stronger than the other. And if that was the case, then that steel ball would move towards the stronger magnet because that pull would be greater than the weaker magnet. Okay, so go ahead and turn to the next page, page 496. So on the previous pages we were talking all about how forces affect motion. You know, the movement from one place to another, or the position of an object. Now we're going to talk about how do forces affect acceleration. So how fast or how slow, a change in direction and speed of an object. Do you swim? Some of you I know do. If so, you know you must push harder against the water to swim faster. Do you run? To run faster, you push harder against the ground. The size of a force affects an object's acceleration. And remember, acceleration is a change in movement or speed of an object. I'm sorry, in direction or speed of an object, not movement. A greater force gives the object more acceleration. So if something is pushing or pulling harder on an object, that means it's going to cause more acceleration. The mass of the object matters too. If you apply the same force to an object with more mass, that object accelerates faster. Forces add up. Look at the diagram below. So let's look at it while I'm reading this. In that first drawing, that very top one person pulls the load. We have a big pumpkin and there's one person pulling it on like a wagon. The load accelerates, which means it changes speed and it changes direction. So instead of just sitting there doing nothing, it's moving a little faster in the direction of that person pulling that load. In the second drawing, so in the middle, two people pull the same load. So we still have the one pumpkin, but now there are two people pulling on that pumpkin. Now it accelerates twice as fast because there's much more force with two people pulling than just one person. So it's going to accelerate twice as fast because two people exert twice the force. One person exerts some force, two people exert 2 times the force. So that's that applied force. We see, let's look at the pumpkin. Above it we have a green arrow that shows acceleration. And then we have a red arrow that shows applied force. Applied force is the amount of force on that object. One person puts about 1 arrow's length of force, applied force on that object. So the acceleration is about the same. It goes about the same speed as that amount of force. But if we look at the second drawing, we see that applied force arrow has gotten twice as long because now there's 2 people. So then that acceleration arrow, the green acceleration arrow, has become twice as long. Now, what happens in the third drawing? The same person pulls a load that is twice as large. So we've got one person pulling a load with 2 pumpkins, so it's twice as large. So we can see that applied force arrow is the exact same length as that applied force arrow in the very top. So she's using the same amount of force as in the first drawing. But the load accelerates half as fast because it's twice as large. So that means, just think of it as yourself. If you had to pull a wagon with a giant pumpkin in it, it's going to be kind of hard. It's not going to go super, super fast. Now, if you had a friend that was helping you pull that wagon with that giant pumpkin, it's going to be a lot easier and it's going to move faster. Then, if in that same wagon, again, only you were pulling it, but there were 2 giant pumpkins, then it's going to move even slower than if you just had one, even though you're pulling on it just as hard as you pulled on the one pumpkin. So you can kind of put yourself in this situation and think of what happens, and then that might help you. So let's look at this diagram now. In which drawing is the load accelerating the fastest? And in which drawing is it accelerating the slowest? So in this case, we're going to look at the green acceleration arrows because it's asking us about which one is accelerating fastest or slowest, instead of the applied force. So we can see the fastest is right in the middle, where the two people are pulling the one pumpkin, because twice the force on one object is going to move it faster than only one times as much force, I think I said that right, on that same object. Now, the slowest is that one person pulling the two pumpkins, because they're putting a lot of force on it, but it's so large that it's just not going to move as quickly. Okay, let's go to the next page, page 497. Mass affects inertia. Remember, mass is how much matter in an object, and then recall that inertia, inertia is the tendency of a moving object to stay in motion. Remember, inertia is a moving object is going to stay in motion unless there are other forces stopping it. A still object is going to stay still unless other forces act on it. That is what inertia is, the tendency for that moving object to keep moving and that still object to stay still. Inertia also keeps an object with no motion at rest. The inertia of an object is determined by its mass. Suppose you apply the same force to two objects with different masses. So I'm going to demonstrate it with this marker and this box of chalk. The object with less mass accelerates faster. So what I'm going to do is I'm going to take this box of chalk and this marker, and I'm just going to gently push them. Well, we can see that the object with less mass accelerated faster than the object with more mass. This one, I'm sorry, get down. This object, this very light marker rolled across the table, while this just kind of tipped a little bit and then came right back. It has less, so this object has less inertia, this smaller object. What if the other object has twice as much mass as the first? Its acceleration is half as much. So if we imagine that this was had twice as much mass as this, which it doesn't, it has a lot more than that. But it would accelerate half as much because it's bigger. So if you're thinking it's going to accelerate half as much because it's bigger, so it's not going to move anywhere near as much as this very light marker. The more massive the more massive the object, or the bigger, the more mass it has, the more inertia it has. So the more the tendency to stay at rest, in this case, or if it's a rock if it's a massive boulder rolling down the hill, the more likely it is to keep moving than a small little rock, or in this case, the more likely it is to stay than this marker is. So it's either way. Because this is larger than the marker, the inertia is more. The more likely it is to stay in its place with a small push, whereas this moves a lot faster. But a massive boulder rolling down a mountain is probably going to stay in motion a lot longer than a small little rock, because a small little rock, there's a lot more friction on it because there's a lot more area touching, and sometimes other things can stop it, like a stump or a tree or something like that. So there's different reasons that in that case, that big giant boulder would be more likely to keep moving than that small rock. Consider the wheelchair racers above. Those with less mass might have an advantage. So the smaller wheelchair racers might have an advantage. If they all use the same amount of force, the less massive racers accelerate faster. So those smaller racers, even though the larger racers are putting the same amount of force, those smaller racers are going to move a lot faster, so they have an advantage. This is a case where less is more. And then if we look at the top, if all the racers apply equal forces, who will win? It's going to be the racer with the least amount of mass that will win, because she is going to accelerate faster. Again, if there was a race between this marker and this box, it's the same thing, just like these wheelchair racers. to get across this, the end of this placemat. I'm going to put the same amount of force. I'm just going to tap them both lightly. Well, this one we already know is going to win because it has less mass. So that means it's going to accelerate faster. So let's see. The marker what? Just like we thought it would. Let's look at this fact at the bottom. No force is needed for an object in motion to maintain its speed and direction because of inertia. So that means as long as there's nothing stopping it, no friction, no objects in the way, you don't need to put force on an object to keep it in the same speed and direction. The only thing that is going to change the speed and direction is putting in more force or less force on it, or a force acting on it. Let's do these quick check questions. So the predict question. Peg kicks a soccer ball with a force of 5 newtons. If she uses 10 newtons of force in a second kick, will the ball accelerate faster? Explain. So, pause and answer the question in your notebook. Okay, so we know that the second kick with a force of 10 newtons, a greater force, is going to accelerate the ball faster because she's using the same ball. So the mass of that ball is not changing. So then, obviously, the kick with more force is going to make that ball accelerate faster. If I just lightly kick a ball with 5 newtons of force, it might not even reach the wall over there. But if I kick it really hard with 10 newtons of force, well, it's definitely going to hit that wall and then probably bounce off because that wall is another force pushing on it. Now, the critical thinking question. Bowling balls and soccer balls are about the same size. Why is a bowling ball harder to throw? So pause the video, answer that question, and then play for the answer. So a bowling ball is harder to throw because it has more mass. And we just learned, even though you're putting the same amount of force on those two objects that are the same size, the object with more mass, the bowling ball, is going to accelerate half as much. It's because more force needs to be put on that bowling ball to move it. Okay, let's go ahead and turn the page. Now we're going to talk about how friction affects motion. Remember, friction is that force between the surfaces of the two objects that can slow down or even stop a moving object altogether. So how does friction affect motion? Think of a hockey player skating on ice. One push of her skate sends her sliding. Now think of a student wearing sneakers and standing at a bus stop. Will he slide if he pushes on the sidewalk? So think about it. If you're on ice skates and you just barely push, you are going to slide across the ice. But if you're standing on a concrete sidewalk in your tennis shoes and you just barely push, no. You're not going to be able to slide. So what's the difference? And it's friction. Remember, we learned about this in that last lesson. Ice on a skater's blade has very little friction. There is some there, but there's not a whole lot. Whereas there's a lot more friction between a concrete ground and a tennis shoe. Remember, friction is a force that works against motion. The amount of friction depends on the surfaces involved. There is little friction between steel blades and ice, which means they can move pretty smoothly without that ice stopping them. There is a lot of friction between the rubber soles of sneakers and the sidewalk, which means it does not allow those sneakers to really slide very easily. You can move, but you have to pick up your feet. Why do you need to oil the moving parts of a bicycle? The oil reduces friction. It helps the parts work smoothly together. So if your bicycle chain is really rusty and hasn't been oiled in years and years and years, that means as you're riding, those parts are not going to move smoothly, and you could end up with a really bumpy ride, or you could end up going flying because all of a sudden your bike locks up, but the chain stopped the bike but not you, so then you go flying off into the distance over your handlebars. The oil makes the friction less so that the parts can work together smoothly. So let's look at this picture down at the bottom. We see in a hockey player. The steel skates of an ice hockey player reduce friction on the icy surface. Now we're going to do the quick check, the predict question. Are you more likely to slip walking on ice or grass? Explain. Okay, now what you hopefully did there was you imagined yourself in this situation. If you are walking on ice, you are much more likely to slip because there's much less friction between ice and really almost any surface, not just steel blades, but even the rubber soles of your tennis shoes. There's very little friction, so you are very likely to slip, especially if you're moving too fast. Whereas grass, if it's dry, there's a lot more friction, so you're not really as likely to slip. Now, if that grass is wet, then you're not as likely to slip as you are on ice, but because that water on the grass is kind of acting the same way as the oil on the bicycle parts, it's making the surface more smooth. So there's less friction, which means you could potentially slip. Now, the critical thinking question. Have you ever seen a sign that says slippery when wet? Why would water make a surface slippery? Well, if you're just listening to my answer to the other question, you know this. But go ahead, pause, write your answer, and then play it. Okay, so the answer is water makes surfaces more smooth, which then reduces the friction. Just like the oil on bicycle parts makes those parts work more smoothly together, water on any type of surface makes it, any type of hard surface, makes it a little more smooth and slippery, and therefore there's less friction. Okay, so what you need to do right now is you need to get out your packet for Monday, April 6th. You need to turn past the chapter summary and wanted poster that you are supposed to wait until tomorrow to do because we got a little behind. And then you have independent practice. Make sure, remember, it's only one page, so there is no back. You do not obviously have that to do. Remember, the questions need to be answered in complete sentences. Make sure you answer all parts of the questions. Watch your sentence structure, make sure it makes sense. Some of the answers can be found just by looking at the diagram. There's a better version on page 495. Some of them you may need to look in the textbook around where this diagram is to answer the question. Some of them you may need to think about what you read and use prior knowledge and put them together to come up with a brand new answer. After that, you do have homework. It's the chapter 11, lesson 2 outline. It's front and back. Remember, on that critical thinking question, they give you lots of space for a reason, so you need to come up with a good, well thought out, complete answer. Make sure you write in complete sentences. You can start on that homework as soon as you're done with independent practice, or you can wait until later today. Okay, if you have any questions on anything I talked about in today's lesson, go ahead, reach out to me, FaceTime me, Skype me, text me, whatever, between 1 and 5, and I will help you out.